Alright, so we're talking about translations and vectors today. We're getting close to the end of chapter 7 here, and this should be around December 7th. So a transformation that maps every 2 points in a plane to 2 more points so that the following properties are true. The distance in between the points is the same. Okay? And if we connect the pre-image to the image in both cases, then those line segments will be parallel. All right. So the slang term for this is a slide. We're going to take this and we're going to slide it over here. So all the points move the same distance and they move parallel to each other. That's what this is saying. Or if you slide it this way, it'll be collinear. So if we were to slide PQ directly along that same line, it would be collinear. So that would be a special case. All right. Again, translation is an isometry. Isometry means same measure. So that should make sense. If we just take something and slide it, it's going to be the same size, and it's going to be the same shape. Okay. Here, this doesn't get used very often, but what they're saying is if we do a reflection, the blue, and we reflect across a line, and then we reflect that again across another line that's parallel, the pink, then that's the same, a double reflection like that over 2 parallel lines is the same as taking that original segment and translating it, sliding it across, double the distance in between the 2 lines. Okay? So that's what that's about. It doesn't show up very often, but still. Okay, so let's see what we have to do here. So they're reflecting this triangle, XYZ, over this line to get this triangle over here. And then they're reflecting that triangle over this line to get that triangle. And it says those 2 lines are parallel. It says AZ prime is 3 and Z prime B is 2. Okay, so it says name all the congruent segments. So this is kind of cumbersome, but let's start with A. So what would be congruent to A? Now, alphabetically, so if you think about it, if these are being reflected across here as perpendiculars, then this is going to be a rectangle, this shape inside here. So that means that segment AB is going to be congruent to segment CD. All right? And opposite sides of a parallelogram are congruent, opposite sides of a rectangle are congruent. So AC is going to be congruent to segment, I should be saying segment before I say all those, segment AC is going to be congruent to segment BD. And then here, because when we reflect over, that's going to be congruent on both sides, so AZ is going to be congruent to AZ prime. All right? So I think we've covered all of the A's, stuff that starts with A here. So let's go to B. And we already have BD and AC. It's right there. So really the only other thing to talk about here is BZ prime and BZ double prime segments. All right. And alphabetically the next one would be C. And we're going to get that same thing on both sides here. So CX and segment CX prime. And then D, segment DX prime and segment DX double prime. Okay, so we're doing all right so far. Now the triangle, if you think about it, let's go X. Y, segment XY, that's going to be congruent to segment X prime, Y prime, and and x double prime z double prime, because that side of the triangle will stay the same length as we move across there. And so then alphabetically our next choice here would be segment XZ, and same thing, moving across. And I messed up there, that should be a Y. Y double prime. And this one should be Z double prime. And then finally, Y is a segment YZ, Y prime, Z prime, and Y double prime, Z double prime. Okay, so that was kind of cumbersome listing all that stuff out, but not that big of a deal. So what kind of figure is the, I highlighted in purple already, ZZ double prime EX. So hopefully you all see if we reflect that across, that means these are right angles. So that means that these are going to be parallel. So the top and the bottom are parallel. We have one pair of parallel sides. That makes it a trapezoid. And then some students want to ask the question, is it an isosceles trapezoid or not? And we really don't know. This is congruent to this. We have that in our list here, XZ and X double prime, Z double prime. But this, there's nothing that says this is an isosceles triangle when this side is extended here. We have no idea how this compares to that. So we don't know if it's isosceles or not. So we just need to stop with trapezoid. Now what's the length of Z double prime? Well, if you use that theorem up there, it says that when you do a double reflection like this, it's 2 times the distance in between. So the distance in between is 5, so 2 times 5 is 10. Now you also could have just realized that that's 3 and that's 2, and you could have gotten 10 that way also. Alright, now the nice thing about this question is it just asks us for one pair of perpendicular segments, not all of them. So alphabetically, we're supposed to try to stay with A if possible. So AB is the best alphabetical segment there, and AB is perpendicular to something. I kind of have it marked right here. Segment AB is perpendicular to segment AC. All right, so we have that. Now, in coordinate notation, a translation adds something to the x-coordinate and adds something to the y-coordinate. That should make sense. If you take something, you slide it across, you're adding something to x and you're adding something to y. Now you may be adding a negative number if you're moving it down or to the left. And that tells you what's happening there. So let's see this in action here. So first of all, we want to plot these points. 1, 2, 3, 4, 1. That was R. And then -2, 0 is S. And then, okay, so I went ahead and finished that up real quick and just plotted those other points. Make sure you label them and we're good to go. So now it says use this translation. So this translation, all we're doing is adding 4 to the x coordinates. So this is one of the few transformations that I actually do the points first. Usually I do the transformation first and then I write the points down here. But for this one I actually do this first. So I'm going to add 4 to x, so that's going to be 0. And then I'm going to subtract 2 from y, so that's going to be -3. Now for s, we're adding 4. So -2 plus 4 is 2, and 0 minus 2 is -2. And then t, -1 plus 4 is 3, and then 3 minus 2 is 1. And then u, negative 3 plus 4 is 1, and 2 minus 2 is 0. So those should be our points after we have adjusted for this translation. So now we can place these new points on here. So 0, negative 3, that's going to be r prime. 2, negative 2, that's going to be s prime. 3, 1, that's going to be t prime. And 1, 0, that's going to be u prime. So there we go. So you can see it slid down and to the right. Okay, orientation, we've talked about this before. We're going to do the same kind of thing there. So RSTU. So if you look at that, we have RSTU. So RSTU. So that's going the opposite direction of a clock. So that's counterclockwise. So that is positive. One way to think about that is it's going up. If you start at the positive x-axis and you go counterclockwise, you're going into the first quadrant. First, second, third, fourth. First quadrant. So that's possibly one reason why they consider that a positive orientation. Now, if we look at RSTU, R prime, so that goes like this. I guess I could have done on here. So that's going like that. That's also counterclockwise. So that is positive also. So they both have a positive orientation. So taking something and sliding it, it keeps the same orientation. Okay, let's talk about vectors. So usually when I mention vectors, I talk about Despicable Me. And the bad guy in the orange jumpsuit, remember his name was Vector because he had both magnitude and direction. He had the shark under his living room. Anyway, vector. So let's see here. There it is, direction and magnitude. The symbol is, it's actually not just an arrowhead. It's, well, the symbol is an arrow when we draw it, yeah. The notation is a half arrowhead, like a harpoon kind of. All right, so the diagram shows a vector. The initial point is where it starts, just like your initials are the starting letters of your name. Initial, beginning. Initial is the starting point. Terminal, like if you have a terminal illness, you're not going to make it usually, eventually. So terminal is ending. Initial is beginning. Okay, so the vector named vector PQ is the vector that goes from P to Q, and that's a half arrowhead on the top. Okay, the horizontal component is 5, the vertical component is 3. So we can break vectors down into their component form. So the first letter tells us how far it moves on X, and the second number is how far it moves on Y. It looks like kind of like a greater than or less than symbols, except stretched out a little bit. So that's component form of vector. Okay, so in each diagram, name the vector and write its component form. Okay, so you can tell where the vector terminates by where the arrow is pointing. So the initial point is C, the terminal point is D. So this is vector CD. Use a half arrowhead on there. Component form, so you're going to say what's happening to X. It's going 1 to the right, so that's going to be a positive 1. It's going down 3, so that's negative 3. Now, if we want, we could also write it down in coordinate form. What happens to X, Y? X is plus 1, and Y is minus 3. Now, the directions didn't ask for that, but it doesn't hurt to think about that as well. So hopefully you can pause the video and do these next three actually. Hopefully you can do both of these. Hopefully you can do this one. Pause the video, practice. The more you can do your notes on your own, the better off you'll be, the better you'll understand this stuff. Okay, so no arrow at E, there's an arrow at F, so E to F. Component form, what's happening to X? It's going 4 to the right, it's not going up or down at all, so that's 0. So if we wanted to do this, coordinate form, that'd be X plus 4, and then just Y. I suppose you could put Y plus 0 if you wanted to. That seems a bit redundant, but okay. And next one here, the arrow's at G, so it's H to G. So H, vector HG with a half arrowhead on top there, arrow. Component form is going 1, 2, 3, 4, 5 to the left, so that's negative 5. It's going down 2, so that's negative 2. I want to do this one more time. It did not ask for this on the end here. We're just going over it. So it's X minus 5, Y minus 2. Okay. So, again, let's put this down here. So 1, 2, 3, 1, 2, 3, 4, 5. That's G. 0, 3. That's H. 1, 3. That's J. 2, 5. That is K. Okay, so that is H right here and J right there. Okay, so now our component vector is 2, 5. So this is very similar to example 2. What this is telling us is add 2 to X and subtract 5 from Y. So we could do these things on here. We could go here, we could move it 2 and down 5. But I would just rather add it to the points. So add 2 to that, that's going to be negative 1, and then subtract 5 from that, that's going to be 0. Okay, H, 2 plus 0 is 2, 3 minus 5 is negative 2. J, 1 plus 2 is 3, 3 minus 5 is negative 2. K, so here, 2 plus 2 is 4, and 0. Alright, so negative 1, 0 is right here. That's going to be G prime. H is 2, negative 2. That's right here. H prime. 3, negative 2. That's going to be J prime. And 4, 0. Be K prime. So there is our translation. Okay. And moving along, we have, it says write the component form of the vector that describes the translation. So all we have to do is focus on one point. So we just want to look at what happened to A. So let's see. A was negative 4, 5, and A prime is negative 3, 2. So if we look at what happened Okay, what happened here? That's plus 1. What happened here? That's minus 3. So 1 minus 3. Component form, that's what I did. That's it. Went kind of fast there. I probably should have went slower so you could pause it and try that out. Okay, so the coordinates of a logging site 5, 7. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7. All right, S. Logging site. Truck travels in a straight line from the logging site to a mill at point M, but we don't know where that is exactly yet. It encounters a road detour at D when it is 4 miles west, 2 miles south. Okay, so 1, 2, 3, 4, 1, 2. Okay, so that's where it was headed, and that's where it hit a detour. Okay, so it went like that, actually, from S to D. So that was the first leg of the trip there. Okay. Then the truck had to travel to an alternate route, A, of 4, 3. Okay. So the truck drove from D to A, vector dA. Now, one place that vectors used to be used quite a bit, I'm not really sure now, but with air traffic control. So when air traffic controllers would see planes on their screen, the plane would be a vector. So that would show how fast the plane was moving and what direction it was moving. So you could see if you had, I'm not really seeing that very well, but I was going to do an example on here. So if you had one plane going like this, maybe a jet plane, and then you had a smaller plane here, you know you're okay, because this plane's going way faster than that plane, and it's going to pass in front of it. This is going to take a while to get there. So you could kind of tell if you were in danger or not. So if you had this, maybe, and then you had this, like this might be a little more dangerous. This could be a collision here, possibly. This, you're okay, because this is going to shoot by way faster, and this will still be poking along after that's already passed by. Okay? So air traffic controllers, vectors. All right, back to this question here. So we have, let's get down here. Write the component forms of those vectors. Okay, so S to D. So we have vector SD, and that was -4, -2. And then we had the alternate route, so that was vector dA, and that was 3 to the right, down 2. So that was 3, -2. Okay, now the mill is 6 miles west and 3 miles south. 1, 2, 3, 4, 5, 6. 1, 2, 3. All right, so the mill was 6 and 3, so that was M for the mill. And it says, write the component form of the vector that the truck has to go to now to get back to the mill. So that would be here. So this is going to be 1, 2, 3, 4, 5, 5, 1. So the vector is A to M, and we went 5 to the left, so that's -5, and then we went up 1, so that's going to be 1 right there. Okay. Now we have 2 review questions here at the end from our semester exam that we've given in the past. Not sure what we're doing this year, but we have the distance between M and N, and we have these coordinates. So if you set up the distance formula here, and you have x minus x squared plus Now, I could have switched. I'm going to switch that around. So we can go either direction. I don't really like that x being negative like that. So I'm actually going to switch those. I'm going to do x minus 3. So x minus 3 squared, and then I should do 10 minus 6 squared. Okay, and I know what that distance is. It's 5. Now there's another, you could guess and check. You could plug these numbers in, see which one works, but that's going to take, maybe it'll take longer. We'll see. Okay, now what happens is students sometimes want to get in here and start multiplying this out and stuff, but let's square both sides, and let's leave this alone. Don't mess with that. Let's go ahead and do this though. This is 10 minus 6 is 4. 4 squared is 16, so that's going to be plus 16. Now we square that side, that's going to get rid of that square root, and this side's going to be 25. Okay, I know some of you just want to multiply that out, but don't do that. Now we're going to subtract 16 from both sides. So that's going to be 9. Now, hopefully, some of you have an idea, you're like, wait a second, why don't we just square root both sides now? So if we square root both sides now, we get x minus 3. Actually, we get the absolute value of x minus 3 equals 3. When you square root a variable squared, you get the absolute value. So now we're going to have actually plus and minus 3, and if we add 3 to both sides, we have 3 plus and minus 3. So 3 plus 3 is 6, and 3 minus 3 is 0. And we don't have 6 as a choice, but we have 0. So that's the answer. Now, if that was too rough, what you can do, again, is you could plug those in. You could try, guess, and check, some things like that. Okay. We have an isosceles triangle here. So hopefully we all remember an isosceles triangle means 2 equal sides. Doesn't have to be perfect. 2 equal sides, 2 equal angles. And it says P is the vertex angle. That means it's up here. That means R and Q are down here. Angle Q is 8x minus 3. Angle R is 2x plus 15. What's the measure of angle P? So we got a lot of stuff going on here. So first of all, since that was a vertex angle, these two angles are congruent. So I can go 2x plus 15 equals 8x minus 3. So that's subtract 2x from both sides, add 3, divide by 6, so x equals 3. Hey, there's the answer. No, that's not the answer. That's just x. They want to know what angle P is. So we need to plug this back in here. So we plug it in here. 2 times 3 is 6. 6 plus 15 is 21. So that's 21 degrees. Oh, there it is, 21. No, that's not the answer either. Since it's isosceles, these are both 21. If we add those together, that's 42. Hey, that's the answer. No. The 3 angles of a triangle add up to 180. These two add up to 42. So that's going to be 138. It's about that time. Be good. Getting ready for study for exams. Come to office hours if you need help. Have a good day.